We are introducing Professor Hill, who is professor at the University of Maryland, College Park, with appointments in the Institute of Physical Science and Technology and the Department of Physics, and he is also a fellow of the Joint Quantum Institute. He received his BA in Physics from the University of California, Irvine in 1974 and PhD in Physics from Stanford University in 1980. He is a guest worker at NIST, where he was a postdoc before joining the faculty of the University of Maryland in 1982, as well as a visiting scientist to Lawrence Livermore National Labs. He has held visiting positions with Institute in Venezuela, in France, and JILA at the University of Colorado. Professor Hill's honors include Fellow of the American Physical Society, Fellow of the National Society of Black Physicists, Presidential Young Investigators of the National Science Foundation. His research interests are broad, with publications ranging from high-energy particle physics to atom physics. His current investigations fall into one of the three areas with atomic, molecular, optical, AMO physics, 1. Ultra-fast dynamics and quantum control, 2. Ultra-intense laser-matter interaction and high-energy density physics, and 3. Atom optics and quantum information science. We gather that this year Professor Hill is on leave from the university, as is running an EMO program at NSF with an annual budget of about $20 million. May I now request Professor Wendell Hill to present this.
Well, thank you. It's a real pleasure to be here. And so it's quite nice to be here. Before I start my talk, I thought I would show this little video. As some of you may know, the Ruby laser is 50 years old this year. And so in the US and in Europe and other parts of the world, there has been a celebration. And so this is the last month of that celebration. So I thought I would show a little video here which is going to set the stage for what I'm going to talk about. So let's see how that, hopefully this will work. It worked before.
Dr. Solo, what do you envision the uses of the laser will be by the turn of the century?
In some ways, I can't help thinking that the laser is not very much ahead of where the airplane was around 1910. It would fly. If you talked to crossing the ocean with 100 passengers at the speed of sound, people would think you're crazy, and you couldn't have done it no matter what you spent. Had to develop the whole science of aerodynamics, get rid of the wooden cloth and develop lightweight metals, and you had to have real inventions like the jet engine. Once you got off the ground, the rest of it had to come. Indeed, the lasers that we have now have gone a long way from our early ideas, and they'll go a lot farther. And I think they're going to be good and bad uses, but I hope that the good ones will outnumber the bad ones.
The laser today, in a sense, is a solution seeking a problem. It is here, but its real potential has not yet been realized. Its ultimate uses wait to be discovered. The creation of the laser was an ancient dream come true. The ray of light that heals, the sword of light that destroys your enemies. The laser today stands on a technological frontier, a frontier we're only beginning to explore. Where the laser's fantastic light will shine is a challenge we face as we move into the 21st century.
Well, I think it's fair to say that we are firmly into the 21st century. That video was made about 7 years after the first laser was demonstrated. And at the time, as Contact said there, it was thought of as a solution looking for a problem. And I think today it's faced safe to say that there are many problems in search of a laser, and quantum information is no exception. So what I thought I'd talk about today is to go over some of the history, and some of the history is going to be selected history that I like, but there's obviously a lot more. There's not time to go over everything that has to do with the laser in an hour here. And then link that to some of the quantum information things that have been being talked about here today. Now, the previous speaker talked about issues, and we're going to sort of talk about problems and challenges. I think the next speaker will talk about problems as well, if I'm not mistaken. Okay, so as was said, I'm from the University of Maryland, and when I first heard about this, I didn't really know that there was a collaboration going on between our two institutions. And so it's actually quite a pleasure. And we now have this Joint Institute for Quantum Information, this Joint Quantum Institute is what it's really called, and it's bringing lots of different kinds of people together looking at this particular problem of quantum, not necessarily for quantum computing, but just quantum issues. It's bringing lots of us together from different parts of the world. And it's quite interesting that, 20 years ago, let's say, condensed matter people and atomic physicists would never talk to each other, and today they are working hand in hand. And we even have people who do gravity and relativity talking to us as well, which they never talked to us either. This is quite fascinating. So on this picture are several different cartoons of the kinds of things I'm going to talk about. Here are these are atoms, very cold atoms falling in gravity. Here's a beam splitter for cold atoms, and then we have some funny-looking laser beams here, which we'll talk about here. So here's where we're going to go, and as I mentioned, we're going to do look at some selected history of the laser, and it's selected by me for the things that I think are really cool and kind of neat, but there are many more things. And then I'm going to talk a little bit about quantum optics, and quantum optics is sort of sometimes a misnomer. Not everything in quantum optics is really quantum, but I'm going to try to talk about some things that are quantum, again, related to this issue of quantum computing. And then we're going to look at some examples of things that are relative to what we're really trying to say, related. And then I'll talk about some experiments that we've done in the Joint Quantum Institute, some things that have been done at the NIST, and some things that have been done on campus. Okay, so the laser timeline. So we could go back, probably Einstein's A and B coefficients are really what gets everything started, because at that point we first look at the simulated emission, which is back in 1917. And so before the laser, of course, was the maser, and this was done in Townes' lab. And then Townes jotted down some notes as to how to make this work in the optical range. The maser was an easier problem because you could actually make a cavity which held a single mode or a single wavelength. Where in the optical region, that was not possible, so you had to do some things more, it had to be a little more clever. And so he jotted down some notes. Now, some of you may know that the history was not exactly smooth because it has to do with people, and people have issues. And so the laser was no exception, and there was a graduate student named Gould who also jotted down some notes and actually had the foresight of getting his notes notarized, but he's given credit for coining the word laser, and so this is going to come back in this history. Now in '58, this is when Vishal and Townes actually wrote their famous paper that was published in Phys-Rev Letters on actually how to make the laser. And at Lebedev, they also had some very similar ideas. And now in '59 is when this patent dispute started. And that's sort of a history unto itself. But we're going to try to stick to the science, although I'll mention this one more time. And then the very first laser, this ruby laser, came into existence in 1960. And this was at a lab, Hughes lab. Back in those days, there were many companies in the United States that were doing fundamental research. That's almost vanished today for companies. But back then, this was a big deal, and so this was when it was first developed. Once the first laser was made, then the floodgates were open, and many, many came after that. Now, it's also interesting, for those of you who sometimes struggle with publishers, particularly PRL, Maiman, once he made the laser, could not get his paper published in PRL. Now, this is not the first time, nor was this going to be the last time the PRL has missed the boat. They didn't quite miss it for Bose-Einstein condensation, but they missed it for a different reason. So you're in good company if you have trouble. Now we have many lasers came after that. We had the first application of lasers even as early as just a year later. And then one of the workhorses, the YAG laser, came into existence here a couple years later, and then even diode lasers early on, and diode lasers are everywhere today. Mode locking, this has enabled very short laser pulses, which then has enabled lots of different techniques even today. And then finally, just 4 years after the first invention, which is about 6 years after they wrote the first paper, then Towns and the two Russians were actually awarded the Nobel Prize for developing the maser. Then there was another Nobel Prize for optical pumping. Now, optical pumping, of course, is very important today, and we'll see that again in a few minutes. And then there were other breakthroughs, fiber optics, and the dye laser, of course. Now, the dye laser was huge because that allowed spectroscopy, and then laser spectroscopy took off. Now, in the late 60s, early 70s, lots of different things also happened, and many of them I'm going to skip, so I'll just sort of say some things. But this work by Ashkin at Bell Labs for this optical trapping, this is sort of the start of what has led to the cold atoms. Although he was looking at trapping particulates, not really atoms, but the same technique got people thinking, and it became big. And in fact, this is what has led to optical tweezers, which is huge in biology. Now, in the 70s, early and mid, and all the way through the 70s, particularly in Shallow's lab, and I was a Shallow student, so as part of this, we developed lots and lots and lots of laser spectroscopy techniques. I mean, virtually once a month, somebody had another idea. Not all of them were very good, but there were just lots of ideas floating around. And one of them here was an idea for cooling atoms. And so this was when Shallow and Hensch wrote down, published a paper on how to cool an atom. And Weidlin and DeMalt also had similar ideas. But there were just lots of spectroscopic techniques that came out of Shallow Hensch lab and other labs around the world as well. Another thing at Stanford was the free electron laser by Mayday, and we had fiber optics coming along, the first fiber system, and of course now we have the world length of fiber. And then a few years later, we saw this first cooling of atoms, and then of course cold atoms is big, and well, in my opinion, may play a big role in this whole idea of quantum information, quantum computing. We won't go into whether that will ever happen, but it's pretty big. Now, in '81, because of all these techniques that have developed and the influence it has had over science, then Bloomberg and Shallow actually won a Nobel Prize, and they actually shared a prize. The other half went to Siegbaum, I believe, for electron scattering. But they got their Nobel Prize for all these laser spectroscopic techniques that were developed, which has just revolutionized how we've done science. Now, after the cooling experiment that Dave Wineland was able to show, he was able to cool the atoms with his laser. Then Steve Chu, also at Bell Labs at the time, came up with this optical molasses. Now, he called it a molasses because the atoms weren't really trapped; they were just slowed. But slowed to a point where you can actually see them. So they got very, very cold. And then it was the adding the magnetic field, which was the trick there to make it into a trap. And so you actually could trap these atoms elastically. But really, showing the molasses was quite important. And then the trapping came out of NIST and Bill Phillips' lab. And in fact, the trapping worked so well, the atoms got so cold that it was a big mystery as to why the atoms were so cold. Now we'll see this. It turned out to be because we were thinking of the whole process as a two-level atom that is just with two states. It turns out that the problem is a lot more complicated than that. And in fact, when you take those complications into effect, you can understand why the system works so well. Bose-Einstein condensation came along. Now there's a big gap. Lots of other stuff happened in that period of time. But now the Bose-Einstein condensation came in, and this again, cold atoms led to that, and then this clever idea of this evaporative cooling, which allowed you to get to very, very cold temperatures. And then so this set a whole new standard for what cold is. And superfluid helium we talked about this morning, that was cold. That was very cold. But now cold atoms for what we call thermally cold atoms in a magneto-optical trap, for example, we're talking about within a millionth of Kelvin. But now to get down to the BEC, you're down another 3 or 4 orders of magnitude. You're down into the nano-Kelvin regime. So these things are really quite cold, and then that's why they actually then work as a single wave, a single state. And so we had the cooling and trapping Nobel Prize, followed by the BEC Nobel Prize, and several other Nobel Prizes. This is somewhat unrelated, but another Nobel Prize in laser spectroscopy. And then finally, we had, just last year, there was a Nobel Prize for work in fiber. Now, this goes on and on and on and on. Again, this is just a selected list. There's many, many more things that happen. But I would think it's fair to say that the laser is really at the heart of a lot of these things, and there doesn't seem to be any end to what the laser can do in terms of helping us in our quest for new discovery, which seems to be the hallmark of certainly physics and science in general. Okay, so this is just a laser, and the laser typically has lots and lots of photons, as we call them, a term which is overused sometimes. But in many respects, one can talk about what the laser does and the light that comes out of the laser in a classical sense, except for the fact that you have the stimulated emission. When we look at how the light interacts with matter, often we can treat that classically. But now we want to look at times when we have to actually look at the quantum nature of the interaction. So this goes back even further. We have to go back to the black body radiation here that Planck talked about, and we actually now quantize this radiation field, and we have to quantize the light. And so now the light comes in chunks just like particles. And it was Lewis who coined this idea of photon from this German word, meaning a portion of light. So we can actually talk about light coming in distinct units. And this is where the quantum comes in. And then we have these ideas of these coherent states, and then we go into a non-classical description. So even if you think about the Young's double slit experiment, if you talk about it in terms of light, you can explain that because light acts like a wave. And so that's a completely classical description. So, but to get to a non-classical description, you need to talk about photons. Or actually, in fact, you need to talk about the light having both particle and wave properties simultaneously. So there was a lot of effort in the 50s and the 60s that went into trying to describe a wave function, which is a non-trivial exercise, a wave function for light. And in fact, looking at the coherence properties and all of this was really quite a feat and quite a lot of work. But now the Jaynes-Cummings model is the model which was partly the roadblock, because this is the two-level atom. And so you have atoms, you have two levels in the atom, and you have a quantized radiation field coupling these two. And so this was the model that we based a lot of our understanding on, and still quite an important model. This has been, there's been updates for 2 photons instead of just a single photon, but this is where we're getting really down to the quantum level, 1 photon at a time. Well, it depends on how you want to count this thing, but you can talk about this experiment that was done at Rochester as looking at some of the non-classical nature of light. Again, a lot of what you see with light can be described simply in terms of a classical wave function or classical electrodynamics. But when you get to the non-classical issues, this is where we really are into the quantum optics regime. So we can talk about single photon sources. And there have been lots of them. I mean, they come from trapped ions, they come from molecules, they come from quantum wells, they come from quantum dots, even color centers. And so there are lots of ways you can get single photons. Now, you need to distinguish a single photon from a source which is very weak, that sometimes lets out a photon, sometimes lets out 2 photons. So you really want to have 1 photon at a time. And in fact, what you'd like to have is a single photon on demand. And one of my colleagues, at least, who works in this area, claims he has a single photon on demand as long as your demand isn't too high. You don't want to be too demanding. You're supposed to laugh at some of these. Let me know you're awake. Maybe they're not so funny. All right. So now let's go look a little bit about some examples here that we can see in quantum optics. So I'm just going to name a few. Again, there are many examples that one can look at. I'm just going to talk about some of the ones that I think are really kind of neat. And so here's, and not to say the other ones aren't, but these are just ones that I thought of. So cavity QED. And so this is the idea where you're going to take an atom or take light, and you're going to put it in a very, very tiny cavity. And Purcell talked about if you were to restrict the light to a small cavity, you can enhance spontaneous emission. Now, it took many years for that demonstration to actually be shown in Hiroshi's lab. And then Kleppner talked about, well, if you take this atom and you can put it in a radiation field, you can suppress this spontaneous emission, and that also was demonstrated in his own lab a few years later. So you put the atom, or you put the radiation and put the atom in a cavity, and it really changes things. You have a very strong interaction between the radiation field and the cavity. If you have atoms in the cavity that are radiating, they're strongly coupled, strongly correlated. You can get entanglement between the atoms because when the light comes out, you don't know which atom actually emitted the light. If you get down to the single, I'm going to say this in a few minutes, you get down to the single atom in a cavity regime, then the atoms can do very interesting orbits inside these things. Now, you can go to the strong coupling regime where you can have a single atom in the cavity, and this was pioneered by Walters and Garshing. He has this micro maser, you have photon emitted in pairs. Now, this is another interesting feature where under the right conditions, you can get 2 photons to come out, which then can be correlated in some sense. You can have a single atom laser. And so there are lots of different things that come out of the cavity QED, and that's another one of the types of architectures that may play a role in quantum information, because you can get these entanglements. Now, this electromagnetically induced transparency is another feature which could play an important role, because it could have an influence on storage of information. And so this was predicted back in '86. Olga now is at Texas A&M, at least spends part of her year there, where they've done lots of this kind of work. This was first demonstrated in Steve Harris's lab, And there have been lots and lots and lots of papers since that particular time. Now, one of the things which has come out of this, among others, there's lots of other things, but one of these things that's come out is this idea of slow light. And the idea is fairly simple. And so, if we think of the velocities or speeds of light, there are actually 4 different kinds of velocities we can talk about. Now, the two that we're most commonly familiar with are the phase and the group velocity. Basically, the phase velocity is just the frequency divided by k, and then if you take the derivative of this, you can define the group velocity. But there are other velocities we can talk about. We can talk about the energy transport speed, that is how fast the energy is transported. You can talk about how fast this, if you have a pulse of light, how fast the half width of this goes through. You can talk about the front. And so you remember a wave can be defined as a disturbance, and so you look at where that disturbance first peaks through, and actually a lot of this has to do with this superluminal type of velocities, how quickly this front is moving through. Now generally, in vacuum, of course, all 4 of these move at the same speed. If you go into a linear medium, then generally the phase velocity is faster than the other 3, but the other 4 are all moving together in a linear medium. But now if you go into nonlinear medium, things get quite interesting. And so this EIT here is an example where things can get quite interesting. So let's go back to our 2-level atom. We can have a two-level atom, and we can have a sort of a weak field that couples these 2 states together. Now you get close to this absorption, and then we have a real and imaginary part of the index of refraction. So the imaginary part, of course, corresponds to absorption. And the real part is the index of refraction. Now the group velocity here is how this thing changes as a function of d omega dk, basically. Now imagine you have a 3rd level, C, and we put a strong laser here. Now by coupling this strong laser, we start to modify the whole structure here of the field. And in fact, if you now look at the real and imaginary parts, they look quite different. You can get right here, right on resonance, where we can have a transparency. And so the system now becomes transparent to the radiation field at that particular frequency. But also this modifies very strongly the group velocity. In fact, you can make the group velocity very, very slow, down to kilometers per second. So you get very, very slow propagation of light through the medium. And not only can you get very slow, you can actually store information. So you can store quantum information, you can actually bring the laser pulse to a halt. And these stationary pulses were demonstrated not too long ago in Lucan's lab at Harvard. And this is really I think this is really kind of neat. So the setup was something like this. So we have a couple of lasers. Now we have our same 3-level system here, but now we're going to have 2 strong pulses. One propagating in the forward direction, one propagating in the backward direction, relative to our probe laser here, which is in the red. And he's going to turn these things on and off at different times. So what happens is that, of course, when the probe laser is on, and these are going to be done in pulses now. So you're going to imagine you have a relatively long pulse, so it's not a very short pulse. But you're going to send this pulse through this medium, and you're going to turn on the forward-going pulse. So what happens here is we're going to delay this. So when the forward-going pulse is on, then the light comes into the medium. It's transparent to the medium, but it's very, very slow. And at the same time, it starts to set up it's going to optically pump this medium. So you're going to get these things in the various states. And all this requires a balance of the intensities and all of this, which I'm not going to talk about. But the interesting thing is that if you turn this thing off, then the pulse comes out. And so here the pulse is on. If you turn it off, then the pulse gets trapped inside. And then you turn this pulse back on, and then you get that information out. So this curve number I here is that this is the beginning of the pulse, a little leaks through. You turn this thing off, it gets trapped, nothing happens. You turn this back on, and the information comes out. So you can store whatever information is on the signal that comes into the medium, and you can retrieve that. Now, the really interesting thing is that if you have two pulses, two of these strong pulses, one in the forward, one in the reverse direction, and when they're both on at the same time, you can delay that pulse from coming out even further. So we look at curve 2 here. Right in this region, we're delaying it. Between the blue and the green arrows, when both of these are on at the same time, the pulses are suppressed. The pulse can't propagate any further. And basically, the argument goes that you set up this set of Bragg peaks in here, and so the pulse scatters and it actually can't move. So you have this, what he calls a stationary pulse inside. And so pulse 2 here, as this thing is delayed, it can't get out, and it finally leaks out. And you can make it go in the forward or backward direction. One is a lot more efficient than the other. But here's a way now we can actually store information. And so this is being looked at quite a lot. Now, entanglement. Now, this is a direct measure, directly related to what one wants to do here in quantum information, because now when you have entangled photons, then you have what's so-called these flying qubits. And so you can actually now transmit this information. And, of course, there's been lots of work done on the polarization of light. So you can take the spin of the light. So you can take a photon, an ultraviolet photon, and you take it into a crystal that does down converting, and then we can get a series of pairs of photons of different colors. Now, this is actually false color. But now, right where these bright spots are here, the green, those two spots, these guys are entangled. And so the spin of those two photons now coming off in different angles now are entangled. And so until you measure one, they're not in any state. And once you measure one, the other collapses into the other state. So you have a true entanglement right at these locations. Now this is with spin, and of course that's been done. But there's another thing that one can do here, and I'm going to talk a little bit about how you make this here a little later, that has been shown, is that not only can you do this with the spin angular momentum, you can do this with orbital angular momentum of the light. And so the orbital angular momentum of the light comes about by having light that has a phase that, as you go around the azimuthal angle, the phase changes, very much like what's shown here. So this is a phase change as you go around these angles. And so these give rise to Laguerre-Gauss beams. And in Zeilinger's group, this has been shown to also lead to entanglement. Now, this leads to a different entanglement than you can get from just the spin, because the spin of a photon only has two states. But the orbital angular momentum, now you can have three states. And of course, you can have what's known as the charge of these orbital angular momenta, so it not only can have one unit of orbital angular momentum, it can have 2, 3, or anything you want. So you can have a multi-dimensional quantum state in this case. And so you can do the same kind of experiment. You can still get these entanglements by this parametric down conversion, but now you can get a much more rich, much more complicated entanglement because you have more states to play with. Well, all right, let me just say this quickly. We can store this orbital angular momentum in a medium. Now, this experiment was not done in a quantum sense, but this is a 4-wave mixing experiment where we mix these 4 waves, and basically what happens is that this, let me back up. One of the features of the orbital angular momentum is that if you look at the phase front coming through, as you go around in pi, then the phase is changing. And the simplest case is it changes by 2 pi as you go all the way around. Since it changes as you go around, that means right on the origin there's actually no light because the phase is ill-defined. And so you typically are generating sort of a donut type of laser mode. And so this is the donut mode, and you can look at the characteristic interference here of what the mode looks like. These are what the modes look like. And it turns out that if you can store that information about the orbital angular momentum of the light in a medium. It doesn't have to be a cold medium. It can be a hot medium. This was done in a MOT, but it also has been done in warm gas. And of course, you have to worry about collisions to destroy that. But eventually, you can get that out. So you can put it in and also get that back out. So that's also very interesting because you can use that as quantum memory. We're going to come back to both of these here when we talk about some of the work we've been doing at the JQI. Okay, well, the list goes on and on and on, and there's lots of references here, and if anybody is interested, I can give you these things. And so there are lots of references. Okay, and those are just key. All right, so now I'm going to spend the remainder of this time talking a little bit about what some experiments that we have been doing at the Joint Quantum Institute, some in my lab and some in Bill Phillips' lab where I'm collaborating on some of these. And they're basically going to fall into two categories, and they're going to be somewhat intermingled, so I'm not going to try to separate these things out. We're going to look at atom optics, that is, looking at optics for cold atoms. And this is all for cold atoms, and most of the experiments we have done so far have been on thermal atoms, but we are doing this in such a way we're interested in being able to do these with in the condensed phase. So looking at decoherence is an important issue that we want to be concerned about. And then we've also done some experiments here on the degenerate Bose gases. All right, so let me start off here. We want to look at some similarities and differences here between Bose-Einstein condensate of a gas, superconductivity, superfluidity, and light. Okay? These things are really more related than I thought of before. So I'm going to show you three pictures here. Upper picture here is a picture of superfluid helium. This is a Bose gas, and this is light. And what those three pictures have in common is they're all showing vortices. Okay? This is the vortices in helium, vortices in a degenerate Bose gas, and vortices in a light field. And the interesting thing about that here is that the equation which describes these, actually this one as well, look very, very similar. Now you will all recognize this is the nonlinear Schrodinger equation, and this is a propagation equation for the light field. And they have the same structure. They're all related to the so-called Gross-Pedayevsky equation, and they have the same structure, except that for the degenerate Bose gas and superfluid helium, we have this in time. So this is a Schrodinger equation, which of course has a single time dependence. In the optical case, we have a spatial dependence. So we have this z component, that is the translation distance, takes the place of time. Now, this picture happened to be taken in vacuum, so that's a linear medium. And so in a linear medium, nothing really interesting happens. But in a nonlinear medium, then very interesting things happen. Because there's an interaction between these vortices here in a degenerate gas, as well as in the BEC. In a linear medium, there's no interaction between these vortices. But in a nonlinear medium, these guys interact. And so one thing that would be quite interesting, and things that we're actually thinking of looking into a little more carefully, look at a light field with vortices as a simulator for what happens in a degenerate medium of a real gas. The difference being, of course, this is a massless interaction. The light is a lot easier to control than matter. So there's a real close coupling there. All right, I already said that. Now, what we're going to look at, what I'm going to do here, I'm going to talk a little bit about vortices, not related to this per se, but we're going to induce vortices in a BEC using vortex in a light field. But first I'm going to talk about the vortex in the light field and how we can use that for atom optics. And then we're going to look at some superflow in a BEC and try to relate that back to superconductivity and things. All right, so atom optics. So if you want to have some quantum information in an atom, of course, atoms don't move very quickly. And if you want to have lots of them, we're going to have channels in which we can move these things around. And so there's really a need for some kind of atom optics. And so we've been playing around with that. Now, of course, there have been atom interferometers suggested for a number of years. And so this is one of the motivations. There have been ideas for doing what we call atomtronics, that is, that you can do electronics with neutral atoms, and so we've been thinking about some of those. And if you have, let's say you have a quantum computer made up of neutral atoms, then you're going to want to have some kind of bus to get information back and forth. You can do this with light. In some cases, you actually want to maybe move those qubits back and forth. The light field might be able to do that. Of course, you can have these squids, and you may even have some type of a model for photonics. That is, you can have delay lines and so forth, and you can think of doing these things all with cold atoms if you had some atom optics in which to try to do this. And we're trying to develop some of these things. So there's a need for guides and beam splitters and a way to store these things and circuits and all of this stuff. And of course, a lot of people are talking about putting these atoms on chips, and so you can make a BEC on a little chip with magnetic wires and all of that. We are taking the approach of trying to do this all in free space. Oops, whatever. Trying to do this all in free space. And the reason for trying to do this in free space is that you can make them and break them anywhere. And so we're doing this with these vortices. Now here's a vortex. How do you make these vortex? Well, it's very straightforward. You can take a mask, and this mask has to have the right phase information, and what this sort of branching phase information leads to these kinds of phase fronts. So basically what happens is if you look at the phase as you go around 2 pi, the phase also changes by some multiple of 2 pi. Actually, it turns out it doesn't have to be a multiple of 2 pi. It can be a multiple of 4 pi. And so here's a multiple of 2 pi, and here's a multiple of 4 pi. So you go around, and so this is called having a charge 2. This would have a single unit of orbital angular momentum. This would have 2 units, and then so forth. You can get very large. We've made as big as 20, actually. And these things can actually propagate. These beams actually propagate. We tend, for doing the atom optics, we tend to make these into what's known as a Bessel beam as opposed to a vortex beam. And then that same phase flux now has instead of being flat and sort of a circular ramp that goes up, these things are inclined a little bit. And so these things propagate over long distances. We're talking many meters without changing their size. So it's got limited diffraction. In fact, it only propagates so far, and then the whole thing falls apart. But you can go for many, many meters. And this picture here is taken of atoms. Actually, wasn't done. This picture I did a different way. But basically, what happens is you have one of these tubes around the cold atoms, and you turn the trap off, and the atoms just fall in gravity. So gravity is being pulled down. You can see they don't move. They don't get any larger in the horizontal direction because there's a tunnel there. So this tunnel keeps these atoms confined. And so you can make these nice long tunnels for these atoms, which we've done. Now we generally make these with a spatial light modulator. The spatial light modulator is kind of nice because we can change this in real time. And generally, there are many different kinds of spatial light modulators. The ones that we typically use are made out of liquid crystals. Now, liquid crystals turn out to be very, very slow. They can't change very fast. So they're on the order of tens and hundreds of milliseconds is sort of the time scale over which you can change it. But nonetheless, you can actually change these things in real time. And here's a picture down here in the corner where we've made these tunnels. In fact, we've made these things. We had 2 tunnels. We're moving them back and forth. And this is being done by simply changing the phase front here. And we can make these things change in real time, and these atoms will move with them. And so just let me remind you of the cold atom here. Basically, this is the typical structure of an alkali. If you tune your laser to the red of the resonance line, the atom, which then has an induced electric dipole, tends to be pulled into the laser field because the laser field has a non-uniform distribution, and so it wants to be pulled into the more intense part. If you tune it to the blue, it gets pushed into the darker part of the beam. And so if you have a hole in your beam, you can have your atoms sit more or less in the dark, which is quite nice because then they don't scatter light quite as much. And so that's what we do. Now, we've been successful in making beam splitters and delay lines. Here's just a simple cartoon. We can cross 2 of these things. We can turn them on and off at different times. We have our mod here sitting, and then they're inside this tunnel. We can see that some of these, we can turn this so that we can get atoms going down the two different legs of this. We can also then have a delay line. These guys move off in time, and then we still have some trap. So we can actually trap these things, and we can let them out whenever we want. So we actually have a tool for manipulating these cold atoms. And there's a whole array of these things. You can make lots of different kinds of things. You can make these many of these different things. We can have vested. We can have several beams, and so you can make whatever you want. You can also even make things that have these fractional charges where you have holes in these things. Now, these things actually propagate. So they propagate in space, and so you can have sort of arms where atoms come off down to the side. And so there are lots of different possibilities as useful tools. So we've explored lots of these things in the lab. Okay, so we want to do all these things in free space because we can make them in real time. They're compatible with all sorts of traps, and we can move them around. And so we call these free space atom chips. And so that's just part of what we're going to be working on. And I'll come back to see a little bit more of that at the end. But let me start off down another path and talk about some work that has been done recently at NIST. And that is to look at superflow. Now, I mentioned that there's a connection between the condensed cold Bose gas and superfluidity. And one of those is a persistent current. And you can have you can have a persistent current in a superfluid that it will flow without viscosity and will essentially go on forever. And the Bose gas, in principle, ought to show the same kind of feature. So we're going to look at that. Now, in superconductivity, then you can have these persistent currents as well. You have a superconductor, so you have this current that flows, again, without resistance. And then you can make, if you have a Josephson junction in these currents, you can make these squids, okay? Now, of course, in electronics, you have charges and you have magnetic fields and all of that. Well, then how do you get a magnetic field in the neutral case? Well, it turns out that if you have a barrier that's blocking this flow of the Bose gas, so we have a junction, you have a barrier, so now you have a partition through which it has to tunnel. If you move that barrier and you go into this moving frame, then you can write down a term that looks like a magnetic field. And so in principle, you should be able to make a squid out of these condensed persistent current of Bose gas. So let me talk about where things have gone so far. So you can, how do you do this? So let's talk about the persistent current first. How do you do this? Well, as I showed you a while ago, that if you have your laser tuned to the red of a transition, then the atoms feel forced to pull them into the intense part of the beam. And so you can first take a sheet of light, and so this can be your chip if you like. So you have a sheet of light, which is very, very thin, and so you can focus, it contains your atoms. And these atoms are very, very cold, so your intensity doesn't have to be too high to hold the atoms in. So they're held in this sheet. And now, on top of that, you're going to put one of these sort of donut modes in here. Okay, so this is in this case, has a charge 1, and so it has a hole in it. And so your atoms now will see a deeper potential where the two red beams overlap, and so the atoms are going to get trapped right in that area. And then by manipulating the thickness of this, you can go from a 3D design down to a sort of quasi-2D design. And there are all sorts of other types of things you can look at for that, but we're not going to worry about that at the moment. So here's some pictures of Bose gas trapped in this potential. Okay, so they're sitting right in this ring. And the hole is there. It's an artificial hole. It's not that it's rotating at this stage. It's there because the potential is higher. So the gas just fills into where the potential is lowest. So how do we get this thing circulating? Well, you can do this by a Raman transition, which we heard about earlier today. And you can do a Raman transition where you take one of these as a Gauss beam. That is, one of these has this orbital angular momentum. and the other is a standard Gaussian beam. So if you do this Raman transition, you can actually induce this circulation in the gas without transferring the gas, making the gas have any momentum. And so that's what's done. And in fact, so it's sort of the geometry of how all the beams come together, and so you got to have all your optics set up properly. But you can actually get this thing flowing. How do you know it's flowing? Well, all right, so here's what the potential would look like. So the atoms sit down in this ring, and so that's what it looks like. If you don't have it flowing, how do you see these things? Well, this is very, very tiny. We're talking about a micron or less. Well, a few tens of microns or less. And so it's very, very tough to see unless you have a microscope, which we didn't have on this particular experiment. So what you do is you let this thing expand. If this is not flowing, what happens is the hole fills up. And so you can see this hole goes away. And so this is how we can actually tell if we have a persistent current. And so if we come down here to a case where there's no circulation, you look in long time scale. This is 40 seconds. That's a long time. There's no hole when there is no flow. But if this flows, this hole stays put. And for the same reason, it's moving around, so the phase is changing. And so the hole has this phase, this continuity in it, and so you have this persistent flow. So this is really a persistent flow in this gas. Okay? So that's the one thing. So that's pretty good evidence for persistent flow in the Bose gas. Now the next thing is to try to put a barrier in here. You can put a barrier in here by just introducing another beam of light, and you can introduce a blue detuned beam of light. Remember, the blue detune now will kick the atoms out, so they want to go away from the blue area. And so this experiment was done by many steps, but we put a barrier in here at a certain point. We turn the barrier off, we turn the trap off, and we let this thing expand, and we look to see what happens. And so one wants to look for several things in this experiment. First of all, we have a persistent flow. If the barrier gets too high, it's going to break the flow. So in this case, the flow is measured as a function of the barrier height. And this is what happens. And so these open triangles here are the measurement of, this experiment was done many, many, many times. And so a barrier height was set, and then one looks to see when the persistent flow breaks up. And so as the barrier height increases, then we eventually break up the flow. But now you can increase that flow by changing the number of atoms. If you have more and more atoms, it turns out that the flow gets higher and higher, and then it turns out that the speed of sound also increases with the number density. The chemical potential goes as the number, so one can change the chemical potential. The speed of sound goes up, and so you can break through that barrier. And that's what's happening here. So at low chemical potentials, with the barrier in place, you can't break through, so the persistent flow breaks down. As this chemical potential increases, the speed of sound increases, you break through, and you come up, and then you have this persistent flow breaks through that barrier. And so one can measure the breakthrough as a function of barrier height. And it turns out to be almost linear. It's not quite linear. If you do a real simple toy model, you can see that there's a small curvature to it. But over this small range, it's basically linear. And this has a slope in this particular case of 1.6. Again, by this simple toy model, if you had a simple rectangular structure, then you would expect that you would calculate that to be closer to 1. Because we have sort of this harmonic potential is in there, it sort of changes that. So that slope is sensitive to the potential in which these atoms sit. So one can actually see these things. And if you compare that to what you would expect, this gray range is where you would actually expect the flow to break down. And basically what happens is that once the flow is higher than the sound speed, it can start to break through. And if it's below the sound speed, it has to stop. And that's because since this is a persistent flow, and since it is a superflow, then the flow has to be quantized. So either it can make it through or it doesn't, and then that's why you end up with this, basically this quantum jump. So it can't make it through, and then suddenly it can make it through, and then you have these quantum jumps. So as I mentioned, these experiments were done in this potential that was harmonic, that looks like this. If we go back to the atom optics things I talked about before, we're also interested in trying to make more unusual potentials, where you can have different shapes, for example. In this cartoon, you can have this sheet, and you can overlay on that other types of potentials. And these were done for doing interferometry, but you can have all sorts of different kinds of potentials. So let me go back. Let me show this one first. For example, you can have interferometry, and so in this particular case, we would have a blue tuned beam, so it would be blue out here, and so the atoms would be trapped here in the colder range. So you could have you can look at these persistent flow type things. You can actually use some atomtronics or a battery or a capacitor or something. Now, the way we make these is really kind of interesting. We use a technique called phase contrast filtering, which allows us to actually put the actual image we want on, again, our spatial light modulator. And since we are using lasers, and since the lasers are coherent, then we run into trouble with speckle in the focal plane. And so the speckle turns out to be of low spatial order. And so one can get rid of a lot of that speckle, if not all of it, by using a phase contrast filter, and you could basically, it's sort of like the double slit problem, you can get rid of this. And so we can end up with a really nice image here in the output. And so the images now, right direction here, are actually quite good, and especially when we blue detune it. When we're to the red, there's still some ripple on top, but when we're blue detuned down at the bottom where it's pretty dark, it's actually pretty good. And so the atoms can move in a fairly smooth potential. Not only that, one has a fairly sharp line, and the sharp line can be dictated and changed by changing the intensities and changing some of the features. And so we could, in fact, make fairly steep potentials instead of the harmonic potentials that we generally have. And so you can think in terms of making a square wave potential and all sorts of other potentials in which we can have, we can look at these persistent flows and things. And so we're exploring how to make those things at the moment. Okay, so let me just show you the people who were involved. The persistent flow work was all done at NIST, and all of these people were quite instrumental in that. And they all, I think, twisted knobs except for probably Bill. And then two of us at NIST were collaborating on that experiment, and they didn't let us twist any knobs either. The atom optic work were done in my lab, and here are two students, two former students here were very instrumental in putting a lot together, and these two new students have taken over that work. And we're hoping to be able to reproduce some of this BEC work, which and over here with these other new type of potentials.